This is what a spectroscope actually looks like, where the light actually comes in through this little opening right here, and then there's a diffraction grating in here which splits up the light, and then you actually look in through that end right there, which is kind of what was happening on the video footage. So now that we have looked at the emission spectra, what I want to show you is focused on the back page of your chemistry reference tables. That would be this lovely document right here. Because on this, there is the Bohr model for the hydrogen atom. And what you can see on this chart is this shows the different energy levels that an electron can be in within the hydrogen atom. So you got the first energy level, then the second, the third, and the fourth, and the fifth, and the sixth. And hydrogen, as we know, only has one electron and one proton. So that one electron, it can jump up into any energy level that it likes, and then it can fall back down. And as it falls back down, making these particular jumps, it emits various wavelengths of light, either in the infrared or in the visible spectrum or in the ultraviolet. And it emits very specific wavelengths. This is kind of like a little fingerprint for an element, and each element has its own unique combination. But you need to be able to interpret specifically what happens with hydrogen. So for instance, if an electron in the hydrogen atom makes a transition from n equals 3 to n equals 1, right? So that would be this transition right here, going from the third energy level to the first energy level. You can see that that emits a wavelength of 103 nanometers, which is ultraviolet radiation. On the other hand, if it goes from the third energy level to the second energy level, that's 656 nanometers. So if it goes from n equals 3 to n equals 2, that is 656 nanometers, which is visible light. And if an electron went from, say, the sixth energy level to the third energy level, that would be this transition, which is 1094 nanometers, which is infrared. Now, the only things you're capable of actually seeing is the visible light. So I want to focus on the 4 visible light options that we have. So depending on the transition, you can get 656 nanometers, you can get 486 nanometers, you can get 434 nanometers, and 410 nanometers. Now, where this gets confusing, we have the state of North Carolina to thank when they created these reference tables, is that up here, this gives your measurement in nanometers. Down here, it gives the electromagnetic spectrum in meters. But if we were to convert nanometers into meters, 656 nanometers becomes 6.56 times 10 to the negative 7th meters. This becomes 4.86 times 10 to the negative 7th, 4.34 times 10 to the negative 7th, and 4.10 times 10 to the negative 7th. You don't need to really concern yourself too much with how to actually make those conversions. What you should be able to see is, what you should be able to see is that if you look down here at visible light, you have these ranges in nanometers for color. So for instance, for the first one, the 656 nanometers, or 6.56 times 10 to the negative seventh, well, 6.56, that's going to fall between 6.5 and 7. So that would be red light. The 4.86, that would fall between 4.2 and 4.9. That's where 4.86 would fall. So that's blue. The 434 also falls between the 4.2 and the 4.9. That's also blue. And then the 410, that falls in the violet range. And if you go back and you check out the video clip of the hydrogen emission spectrum, you'll notice that there is a red line. There is what appears to just be one blue line, but it's actually both of those together. And there is a violet line that's visible on that spectrum. So this is pretty much what you should be able to interpret today. I'm going to give you a few questions about this. The key thing to note is that the energy is released as the electron falls back down to the lowest energy level, not as it moves up. It absorbs energy as it moves up to a higher energy level. It releases energy in the form of electromagnetic radiation, including some visible light that we can detect. If you were capable of seeing ultraviolet radiation like some insects are, you could see these lines up here in a spectroscope. We have computer and camera sensors that can detect that, but your eyes can't.